In this video, we will discuss concavity, another very important property of the graph. So suppose you have a function, right? You have a function y equal to f of x, right? Suppose your function is increasing on interval. Similarly, you can do the decreasing version. On interval from a b, the function is increasing from a f of a to b of f of b, right? And there are two ways the function go up to b f of b on this increasingly go to the next number, right? This is a f of a, this is b f of b, right? This is x, y, x, y. One way to do that for sure is a function increasing very fast in the beginning, then slowing down, right? The other way here is a function going slow first, then speed catch up and go up to that point, right? These two are different, very different. You can see that on the first one, if you try to sketch a tangent line at any point, the curve is always below the tangent line, right? And if you try to sketch a tangent line on the second kind of increasing pattern, the curve is always above the tangent line, right? So we have two definitions for these two things happens, right? So this the first one is called concave down. Concave downwards, right? Concave downwards. And the second one is called concave upward. Concave upward. Let's write down the official definition for that, right? So concave down here means the graph is not only happens, you have increasing, sometimes decreasing also, right? The graph of f here lies below all is tangent line on the interval, right? And for the concave upward, which means the graph of f lies above all is tangent line on the interval, right? So that's what happens. You have concave upward and concave downward. And let's try to decide, right? How do we determine you have concave up intervals and concave down interval, right? So the full name for this is should be f here is concave downward on AB, on this corresponding interval, and f is concave upward on AB, right? How do we decide it? So if you try to sketch a few tangent line, you can see that the tangent line starting from very steep slope and going flatter and flatter, which means f prime is which means the slope is decreasing, right? Slope is decreased to a smaller number. And what's the meaning of that is a second derivative is negative, right? So you can see that in this case, the slope of the tangent lines is decreasing, decreasing, decreasing. And I dot E, because slope is f prime, right? And I dot E, what happens is f double prime is negative. And very similarly, in the concave upward, so if you try to sketch a few more tangent line, you can see that the tangent line is getting steeper and steeper as x getting larger and larger, which means the uh, the slope of the uh, the tangent lines is increasing, right? Getting bigger and be greater and greater, right? Because right, because the tangent line is getting steeper and steeper, right? So f prime similarly is f is the slope, right? Slope is increasing, which means the second derivative is positive. I dot E f double prime is positive, positive. So this is our concavity test, right? Let me try to write that down. So that's this is our definitions, right? We have two definitions: concave upward and concave downward. And then we have what the concavity test. How do we decide concavity test? How do we decide the function is either concave upward or downward, right? And the first one here is f double prime of x if is greater than 0 for all x inside I is our interval, right? Then the graph of f is concave upward. I would sometimes just say concave upward, right? Up and on I. And if B here, if f double prime of x is less than 0 for all x inside I, then the graph of f is concave downward on I, right? Concave upward, something look like this. Concave downward, something look like this, right? So that's how do we sketch it if you have a concave upward or downward, right? Let me use blue for a second. Okay, so let's see an example, right? And also another thing here is if the concavity changes at a point, right? Because go from positive on to negative, this for sure at a point the concavity will change. So if the concavity changes, we call that at a point. At that point is called inflection point, right? So inflection point is the point at which concavity changes. So either change from concave up to concave down or concave down to concave up, right? So let's try to do an example. We finish our example from the increasing, decreasing part, right? And we have a function f of x equal to 4x cubed plus 3x squared minus 6x plus 1. So using our first derivative test, we know that this function has two increasing intervals, intervals, which are from negative infinity to -1 and from 1/2 to positive infinity. It has a decreasing interval, which is from -1 to 1/2. So the whole how do we get it? It was introduced in a previous video on in the concept increasing, decreasing, and also critical numbers, right? And so also we know that f of -1 here is a local in maximum value, and f of 1/2 is a local minimum value. And also we know the derivative of this function is 12 x squared minus 6x plus 6x plus minus 6, right? So that's the derivative of this function, minus 6. Now we want to know, the second part, we want to know the interval of concave up and concave down. Let's try to do that. So decide concavity and also possible, if you have one, possible the inflection point. So to do that, we need to get the second derivative. So f double prime x. And if you use our previous, this is very easy function to differentiate. So this should be 24x minus 6, right? Plus 6. So this is 24x plus 6, right? And so you can see that f double prime of x equal to 0 when x is -1/4, right? So that's an easy equation to solve. You get two intervals, negative infinity to -1/4 and -1/4 to what? To positive infinity, right? So what? So you can see that when x is less than -4, this is negative, right? F double prime is less than 0, which means f here is concave downward, right? The graph of f is concave down. And f double prime x, when you have x is from greater than -1/4, this will be positive. Then f is concave upward, right? And so you get concave upward and concave downward. And do we have inflection point? Yes, right? It's this number when the second derivative equal to 0, left side concave downward, right side concave upward. So that's a point at which concavity changes, right? So -1/4, f of -1/4 is an inflection point. Inflection point. Right. So we get three special points: one local maximum, one local minimum, and also we have an inflection point. And we know all the increasing, decreasing things, right? So you need to figure out the function values, right? So let's try to sketch our function. We have three special points when x is -1, when x is -1/4, when x is 1/2, right? 1/2, right? F of -1 is a local maximum value, right? F of -1/4 from -1, 4 is an inflection point. So this is our inflection point. Alpha 1/2, this is alpha 1/2. So this is a local minimum value, right? Now we are ready to sketch it. We know that from here to here, increasing, but concave downward, right? Concave downward. So it's something like this. And from -1 to -1/4, so this is decreasing, still concave downward, right? So it's something like this. And from -1/4 to 1/2, still decreasing, but concave upward, right? And go, no, sorry, that's wrong, right? Not to 1/2 to the actual point. Oh, wait. And from 1/2 to infinity, the function is increasing concave downward, upward, concave upward. So this is our the function schedule the function y equal to what? Where's my function? The function is 4x cubed minus plus 3x squared minus 6 x plus 1. So this is how do we using the first and second derivative the function to get increasing, decreasing local maximum, local minimum value of the function, and also concave up interval and concave downward interval, and also the inflection point. After we have all the information, we can sketch the graph of this function, right?